Okay, so today's going to start the second part of our 7.1 lesson. Last time we spent most of our time talking about discrete random variables. Today we're going to talk about their counterpart, continuous random variables. And again, the word tells us kind of what's going on here. The values for a random variable could take any value between a certain given interval. All right. So let's take a look at this example here. It says let S be all numbers x such that it's between 0 and 1 inclusive. That means it could be 0.5, it could be 0.75, it could be 0.999999. It could take any value along that interval there. Well, if that's the case, then how do we go about assigning probabilities since there are infinitely many possible values? Because we can't go ahead and write a probability distribution because there's an infinite number of x values here. So we have to find some other way to represent what's going on here. And what we do is we use the area underneath a density curve. Because what we want to understand is that the area underneath the density curve is equal to the probability of that outcome. And be careful in the way you read that, because when I talk about any specific value in a continuous random variable, the probability of any one value is always going to be 0. But when we're talking about along a certain range within that interval, well, then we go about finding that probability by finding the area underneath that density curve. Now we need to remember a few things about density curves. First is that the area underneath it is exactly 1, and that's going to go ahead and match up with the total probability of 1, or 100% of all possible outcomes there. So if we think about that, we need to know one of two things. If we're talking about these density curves, we need to know the function that defines the curve. Now, thinking about that, that should ring a bell as to something we've talked about previously in the course, specifically something like the normal curve. When we talk about the normal curve, we're talking about the symbols here, notation. N stands for normal distribution with a mean mu and standard deviation sigma. Well, we recall that's what we have there, with the mean right there in the middle, and the standard deviation is going to occur at the first point of inflection there. So we can see that is the distance of sigma. Okay, but that's just recalling what we already know about normal curves. All right, we also should know how to find the z, the standardized value for a normal distribution, given in this formula here. Z equals x, meaning the observation, minus the mean over the standard deviation. And if it's not something that we already know the function that defines the curve, well, then maybe it's something that's a very simple function in which we can use simple geometry to compute areas. Now, when we say a simple function, maybe that's something like a uniform distribution. Well, a uniform distribution is a situation where each outcome is equally likely. Maybe you're thinking about the idea of, well, the situation is kind of blanking me right now, but it's just something where every number is equally likely. Let's say you're choosing a random number between 0 and 10. Well, getting 5 is just as likely as getting 8, is just likely as getting 2.72. All of those values there are all equally likely to occur. That would be an example of a uniform distribution. But it doesn't have to be uniform. It could also take the shape of a triangle, or maybe just a sloped line. Okay? This here is another situation where we're talking about a continuous random variable, and this is kind of showing us a visual of how to find the probability of event A, as this is referring to here. Now, if we look at it like this, we could take this, and right now, since this is not a calculus-based statistics course, if we were to try to find the area underneath this curve, we would probably have to try to estimate it using some kind of shape here, some geometry shape like a trapezoid, and then we could take the width, let's just call that x and that y, and then we would take the width here, y minus x, we would find the area of the rectangle, and then find the area of the triangle as well, and then add them together, and that would give us the probability of this event A occurring. Of course, if we knew our calculus, we could just take the integral over that interval and that would give us the probability of that event happening as well. One thing we want to note here is that when we look at this equation on the bottom right, it says the probability that x is greater than a number is equal to the probability that x is greater than or equal to a number. The difference being on both sides, obviously, the inequality symbol. What this is saying is that it doesn't matter whether you include each of those individual values. In this case, I showed them as x and y. Because, well, it doesn't change the probability. If you think about that, the reason for that is because the probability of any single event in a continuous random variable is 0. There's no physical area underneath a point, and since the probability is the area underneath a point, well, that's going to be 0. That's a pretty important concept. Definitely make sure you have that down in your notes. This is an example of a uniform distribution. The first thing that we can do is take a look at it and confirm that it is a density curve, because it kind of looks different. But if we look at it, here it is. We're saying we're choosing a number between 0 and 1. And what we're looking at is the fact that it's a density curve. Well, if we think about that, the area is equal to the length times the width. The length, meaning the horizontal distance there, is going to be 0 to 1, so that's 1. The width, we'll call that the height in this particular case, that's also 1. That goes ahead and gives us that area of 1, confirming that it is in fact a density curve. And as the question pops up there, it doesn't matter if we use less than versus less than or equal to. That's referring to our first question here. Well, we kind of just went over this on the previous slide, but no, it doesn't matter, because the probability of either one of those events, meaning the probability that x is exactly 0.3 or exactly 0.7, is 0. So again, we're just looking at the area between them. The inequality symbol, whether it's less than or equal to, does not matter. So we're going to find these two probabilities on the next slide here. And it'll be a very visual approach to finding these probabilities. The first one here, the probability that 0.3 is less than or equal to x is less than or equal to 0.7. Well, here we have it right there. This is a reproduction of that same density curve we had. And all we're doing is we're looking for this area in between 0.3 and 0.7. And it's a rectangle. So all we have to do is do the, oops, sorry about that. All we have to do is find the area, which is just going to be 0.4 on the horizontal and 1 on the vertical. We have 0.4 times 1 gives us that area of 0.4. In other words, 40% of the time, we'll find a value between 0.3 and 0.7. Now, that being an and compound inequality, if you remember your algebra, number 2 is not an and, it's an or. And if we look at that, okay, well, no big deal. We're looking at the probability that is less than 0.5. So that's this area here. Or greater than 0.8. So we're just going to find these two probabilities and add them together. All right, well, on the one on the left, we have 0.5 for the width. 1 is the height. So as you see there, that area is 0.5. For the one on the right, we have a width of 0.2. Also a height of 1, giving us an area of 0.2. And if we add those two together, we end up with a value of 0.7. Now, alternatively, we could have found the area between those two values. And since that's the area we don't want, we could have just taken that away from 1. And that'll work just as well. Your choice on that situation. Let's say we had a different density curve, and this one in particular is, say, generate two random numbers between 0 and 1 and take y to be their sum. Y to be their sum. That's what gives us this triangular shape here. And if you think about that, well, it's the same idea as if you were to roll 2 dice and take their sum there. You're more likely to get a sum of a 7 than you are to get a 0 or a 2 or a 12. Excuse me, you can't get a 0 when you're rolling 2 dice. So the numbers in the middle are much more likely to occur because there are many more ways that you can get that number in the middle. Well, the first part is asking us to just verify that the area underneath the curve is 1, just like we did in the uniform distribution there. Well, the fact that it gives us the height of 1 here is what we're going to use. We're going to use the height is 1. Obviously, the width is 2. And recalling what we know about triangles, the area is 1/2 base times height. So it's 1/2 times that base of 2 times the height of 1 gives us an area of 1, just as we expected to find since we did call it a density curve. The next question is asking us to find the probability that y is less than or equal to 1. Probably don't even need to do the math on this one, because as we look at that density curve, well, we have half what's going on. But we could do the math as well. Again, that's a triangle, so it's 1/2 the base, which is 1. The height is also 1. So 1/2 of 1 times 1 is 0.5. No big deal there. Our second situation is a little bit more complex. We're looking at the probability that y is less than 0.5. And the tricky part here is, well, we know the width is going to be 0.5. But what about the height? Well, if we think about it, since we have an isosceles triangle here with the width of 1 and the height of 1, well, what we have going on in the smaller blue triangle is a similar triangle, and that means that the ratios are going to stay constant. So the height of that triangle is also 0.5. So now we have a half times, really a half times a half. That should be a half there. We have a half times a half times a half, which is 1/8 or 0.125. Sorry about that typo. In other words, 12.5% of the time will our y value take a value of less than 0.5 there. Okay. So those are two situations where we had the very simple geometric probability function, that we had to find the areas for, and you could imagine it going in a couple of different ways as well. But what we want to spend more time with is what happens if we have a normal distribution. Can we find the probabilities for that? And really we should be able to, because we've already done it back in chapter 2. Now we're just applying it to this different concept of probability and what that means. So this example here says, cheating in school. A national survey revealed that 12% of students say that they would report a fellow classmate to the teacher if they saw him or her cheating. And it says here that this distribution follows a normal distribution with a mean of 0.12 and a standard deviation of 0.016. So that's what we're referring to as the national probability, okay, the true population probability. And then it says, if you ask this same survey to students at Freehold Township High School, what's the probability that the survey results differ from the truth about the population by more than 2 percentage points? So there's our important phrase there, more than 2 percentage points. So that means it has to be less than 10, okay, say x is less than 10, or x is greater than 14, because that's going to mean that it will differ by more than 2 percentage points. All right? And since these are in proportions, I should say 0.10 and 0.14. So let's go ahead and get ourselves into the problem. It says because p is 0.12, the survey misses by more than 2 percentage points if p hat is less than 0.10 or p hat is greater than 0.14. This is our first situation looking at that p hat that we're going to be spending more time with later on. We've seen the y hat, which is just an estimated y value. We did that with linear regression. When we're talking about p hat, we're talking about here an estimated proportion. Can I spell? Not really. Okay, estimated proportion. Because we don't know the true national proportion, we're just looking at this sample and trying to estimate the true proportion. Okay, so this is our statement that we're looking at. The probability that p hat is less than 0.10 or greater than 0.14. Another way to look at that is really to look at saying 1 minus the probability that it's between 0.10 and 0.14, and maybe we should draw the situation here to see it a little bit better. Here we have 0.12 in the middle, 0.10 and 0.14. What we want is the area on the outsides, and we could find it that way. We could find the area to the left of 0.10, to the right of 0.14, or, as we're seeing in this statement here, we could just find the probability in the middle and subtract it from 1. Really your call. In this case, I would prefer to find the area in the middle and subtract from 1, but it's up to you. So the first thing we need to do is we need to standardize each one of these values, and that's what's going on right here. We see our x is 0.10 minus the mean of 0.12 over the standard deviation of 0.116. That's standardizing the 10% value, and we also have to standardize the 14% value over here, and that's going to give us our z's. The z's that correspond to that are negative 0.125 and positive 1.25 there. All right, so if you're thinking about this as far as a chapter 2 kind of topic, we're working forwards with this problem here. We're going from x to z to p, okay, working forwards, x to z to p. And when we do that, okay, we're looking at now the probability that corresponds to the positive 1.25 is 0.8944, and the one that corresponds to the negative 1.25 is the 0.1056. And you might be confused a little bit about what's going on here, but all I'm doing is I found first the probability or the area to the left of 0.14. That's the 0.8944. And then I'm going to find the area to the left of 0.10. That's the 0.1056. And to find the area in the middle, I'm going to subtract big minus little, and I'm going to get 0.7888. But again, that's the area in the middle. Then I have to come in and subtract it from 1 to get the areas to the outside. Okay? And that gives us our final answer there of 0.2112. Now that's doing it by hand using the formulas and the z-table. We could also come in and use the graphing calculator, and if you think this is a normal distribution, so we're going to be using the normal CDF function. Notice we start with the 1 minus, because what we're going to do is we're going to find the area in the middle, right? We say normal CDF low, comma high, comma mean, comma standard deviation. Now, for those of you guys who have the updated operating system on your calculator, you don't have to enter those in with commas there. They prompt you for the low value, the high value, the mean, and standard deviation. But for those of us running on the older system, you do need to do that. So we're going to do 1 minus the normal CDF of the area in the middle. And notice we get 0.2113. Is it slightly different? Yes, it's slightly different. Because what's happening is that the calculator is using a table that is much, much more detailed than the one that we're using with our z-table. Now again, this is all estimated anyway. In order to find a more true value, we would need to do the calculus, find the integral over that interval of 0.10 to 0.14, and then take that away from 1. Okay. This being the visual of what's going on there, again, kind of we drew it on the previous slide, but since it's a normal distribution problem, we should always include that diagram as well. Okay. So that concludes our lesson on continuous random variables. We talked about the simple functions, we talked about the normal distribution, and there's some other things that are going to come up when we get to our exercises in class tomorrow. But you should make sure you have understood this video pretty well, and we're going to come in tomorrow, we're going to make sure that we understand these 3 problems, 7 through 9 on page 475, and then we'll spend more time going into more exercises to make sure that continuous random variables are clear to us. All right, let's see if I can stop this video. And don't forget, as it says here on the bottom, we are going to have a 7.1 quiz coming up very soon. All right, see you guys.